Hello everyone, good afternoon. My name is Zhe Jianpeng. I have been working on recommendation for the past 5 years. First and foremost, I want to sincerely thank all of you here in Seoul Metal Week. It's an incredible honor to be speaking in this vibrant and innovative city. Flying 12 hours from San Francisco, definitely worth it. I'm grateful for the invitation and your presence here today. It means a lot to me. So let's dive into the topic, next generation recommendation, interactive recommendation using multimodal LLMs. So you guys have been hearing a lot of chat-based application today, right? So let's talk about that. So let's talk about how recommendation differs from with modern advancement in LLM. So interactive recommendation system represents a new paradigm, one where recommendations are driven not just by past engagement, but by actual conversation with user. Unlike traditional systems that heavily relies on user engagement data like watch time, click, likes, sharing, and so on, a chat-based or interactive recommendation system can actively gathering information from your chat history, and user have the ability to alter the system or steering the recommendation system in a significant way. Through chat interface, user can express preference, refine suggestions, and steer the experience in real time. Today, I will walk you through how such system works, and including some technical details to improve and core technical challenge to improve such system. And finally, to wrap up, I will share some key trends I'm seeing in the industry and some of my vision how this technology evolves with AI in the past 5 to 10 years. Okay, let's start with the system overview. So as you can see, this is a very simple overview of how this system should work. Everything starts with a conversational chatbot. And there's an information extraction module where the LLM will actively review your chat history and extract key information for recommendation. And finally, they will organize those information and write to a distributed key value storage where user ID will use as a key, and there's a JSON stream that can be used for the recommendation system to act on. And you can see the conversation chatbot, information extraction, and the organized information async read and write components. They should be done offline. And the rest of the components are done online. This design choice is made such that the critical delivery path for the recommendation system will keep a low latency budget. And finally, today's talk will have a focus on the multimodal retrieval using clip model and how I improve that model to bring personalization to this experience. And finally, the retrieved videos will merge with other retrieval source and send to a final fine ranking, which is a personalized fine ranking model. And then finally, this video will be selected for impression to the user. Now, let's review some of the key design principles our team have been thinking about this for the best user experience. Okay, first, we want to have immediate feedback on strong user intent. So this means when you talk to a chatbot, when you express some strong intent on liking something or interesting something, or for example, me traveling from San Francisco to Seoul, the system should be able to recognize my point of interest as Seoul. So he should be able to capture this and start to recommending me relevant content to Korea and to Seoul about the culture and point of interest of the city. And the chatbot should be able to surface this feature intuitively and reflects user intent without explicitly showing the user how this feature works. The user should be able to just look at the For You page or your feed page and have this aha moment, and suddenly know, like the chatting is interacting with the recommendation system. Second key design choice is no additional latency added on the delivery path. As I mentioned in the previous slide, these components can be broken down to offline and online. By having this key value store, this distributed key value store, we are able to have a lot of computation or model inference done offline, such that the online delivery paths are not slowed down. Because this is a very critical component where any drop in latency can lead to drop in top-line metrics. Third design choice is the chat response are natural and human-like. Imagine how your experience is with the ChatGPT, where the word come out one by one. We made an explicit design choice to not do that. Instead, we generate the response at once and make sure to prompt the model to generate concise response so that it feels a little bit more human-like. And finally, the fourth point is generation safety and content safety. This is often overlooked for user-facing application. So this is very important for any user-facing application, such that the content you returned or respond are safe and safe for the user and the community. For this part, we fine-tuned the Llama model to guard user input and model output to ensure content safety. Second, now this is the agent execution DAG for the information extraction component. So as you know, this is a chat-based app, so we use LLM to understand the chat history. And I also mentioned in the key design choice, we want to have low latency overall. Therefore, we break this to multiple large language model call. So if you look at the second layer of this, so you start with key phrase extraction, user intention understanding, information extraction, and the safety check. All those are running with different model in parallel. And the advantage of that is, first, we're able to train, test, and evaluate different model components for each different task, and have a golden evaluation set, such that each component can be iterated separately. Second, we're able to choose the model wisely, depends on the task, such that the most appropriate model are used for each task. After the second layer, there's the task selection layer. That's basically a fine-tuned classification model with different tasks we define. For example, if you tell the system that I want to learn more about Seoul culture, you will recognize learn more phrase and classify this task into have more video about Seoul's culture, Korean's culture. So that's something that is done in the task selection part. And finally, all those information are organized into this generate JSON to control recommendation system. So this JSON string is where what's being written back to the key value store, the big circle part, and being read by the recommendation system in the key delivery path. Finally, the response that to user will send back to keep the conversation going. Now, with this system, I think so far we have a good understanding of this, how this system works. Now I'm going to dive into the key component of this. That's the clip model, where in Able we find relevant videos based on the text. So now, so this is the relatively old paper back by OpenAI in 2021. I will start from here and gradually build up to what we're working on today. So this is how text-to-image clip are trained. It maps, so clip basically is the contrastive learning framework where it maps the text embedding and the image embedding to the same space, such that the text, such that you can search the image using text. Basically, that's what it does. So here, we want to build a text-to-video model, but we can start from a text-to-image model. So initially, this clip model was pre-trained on 400 million text-to-image pair, and the loss function used here is called info NCE loss. The Q and K, the laser is not working, but the Q and K dot product represents the similarity between text and the image embedding. So all the positive pairs are organized diagonally. Actually, the slide's color is not correct. So if you see the slides carefully, the diagonal is blue color. Those are positive pairs. And all the pairs in the horizontal are negative pairs. And those are organized diagonally such that every batch have a positive and the negative pairs and feed into the system. And one thing I want to highlight is this info NCE loss. There's a temperature parameter as the denominator. That's a very important parameter. It actually controls how much the model penalizes hard negative samples. The small tau penalize hard negative more and make the training overall converge faster but less stable. A larger tau smooths out the overall loss function and have slower convergence and possibly underfitting. So actually to achieve the best result, we tune this very carefully There are mainly two ways to do this. One is that we can have this as a trainable parameter. The tau can be a trainable parameter, and the model can learn that automatically. The second way is we start with a relatively large tau and gradually decay it to small tau. This way we can have the model to learn on overall distribution first and then focus on the hard negatives. Either way works. Usually it takes multiple rounds of experiment to find the best paradigm. Now, this is a working solution for text to video because we can just use one image to represent the video, right? The main image. However, this is no way near the optimal solution. From there, we enter the second stage where we added the visual transformer to this component, such that we replace the image encoder to a video encoder. So how are we achieving this? So if you look at the plot on the right carefully, you can see there's the right half, there's a linear projection of feature patch where it maps the image to a linear layer, and then there's a positional encoding. So basically, we sample frames from the videos and then send those images to the vision encoder and add positional encoding to inform the model how those frames line up. Because transformer architecture are intrinsically order agnostic. Without the positional encoder, it doesn't know like which frame comes first. So it needs to have this positional embedding to tell the model which frame comes first. So initially, with this model, we used a constant frame extraction. So think about a video of 10 seconds. We can extract one frame every second. That's a perfectly fine solution and workable, but it's nowhere near optimum because for a video, sometimes the action are more intense in some part, right? So we later adopted a called adaptive keyframe extraction technology where more frames are extracted when there's more action happening. We identify through optical flow. Since that's not the key point of this presentation, so I will leave that part and go to the next section. So yeah, with the adaptive keyframe, we are able to train a well-working clip model, but there's some part missing in this. So going back to the beginning where I mentioned recommendation is all about personalization, right? But this type of training framework itself lacks knowledge in personalization and lacks human preference. Because when we prepare the training data, those positive pairs, they're very similar in terms of like content. Like if you look at, I don't know how many of you consume short-form videos, but if you do, you can see some of them are very similar in terms of visual content. Therefore, it's very hard for the model to learn human preference. And that's where the key part comes in. Like, how do we improve the model to actually bridge the gap? There are two things we have done here. First is that we collect a bunch of unsupervised data in this type of search user phase. When user enter a search query, you will come up with multiple videos. This is very common in many search platforms. And often you will engage with one of the video. That brings us, that gives the system a very clear signal that you have a preference on the video engaged over the field that's shown to you. So this is very valuable data to tune the clip model to capture this human level preference. Because for the video you searched, you know that they're already similar because you enter a query to search them. They're already similar, but now you click one of them, that means you have preference on this over others. So this is another layer of data we use to fine-tune the model. And second layer of data we use to fine-tune the model is we have a human label query to video preference pair. So a human agent is being given a text query and two videos. They will label one positive and one negative, and those pairs are used to form the model fine-tune, to support the model fine-tune. So this is the key method we use to give the clip model human preference. And I think this type of method can be used in other type of model as well, whatever that fits your need in your use case. Now, second point, personalization. So human preference does not equal to personalization. So human preference is how we all think, like it's collected over everybody's pair, but it doesn't represent personalization. Therefore, we add a personalization model to this, and if you look at this plot carefully, in the merge score with U2I model part. U2I means user to item. Item here usually means video. So this is another model that's trained similar to clip architecture, but trained on user engagement data, like clicks, sharing, and comments, such positive actions. And this gives the score for personalization, because user represents you as a user in the platform. It specifically represents you. Therefore, we combine the score of U2I to the clip model to give the system an understanding of personalization. This, in our experiment, this shows it improves our engagement metrics by using just clip model. Now, finally, we have this safety fine-tune for safety component. As I mentioned previously, safety is always very important for any user-facing application. In this case, internally we have a dictionary of unsafe words, and we also have human pipeline, human labeler to label unsafe contents, and we use this as the fine-tune data to fine-tune on the Llama model to make sure the text generated by the GPT model are safe and safe to show the user. So this is another important component. And we also use LLM to generate a lot of new training pair based on the dictionary. So it's kind of like tell the LLM to generate different unsafe example based on the dictionary so that it can better fine-tune the model. So combining all this point, this gives us a well-functioned chat-based system where it actively captures information in your chat history and start to steering and altering your feed page. Yeah, so that's what we have so far. So I want to also talk about what's the implication of this in, say, in the next 5 or 10 years. So first thing I observed is that content consumption is shifting from human-generated content to AI-generated content. So think about how, so just myself, I start to spend a lot of time on ChatGPT daily to ask questions, to ask ChatGPT help me to write stuff or ask for recommendation for attraction around Seoul. So this is a clear direction where the content consumption is changing from user-generated content to AI-generated content. From recent statistics, we already know that Snap's My AI chatbot is available to our 800 million active users, and OpenAI's ChatGPT also have reported surpassed 800 million weekly active users as well. So there's a clear direction where current generation are not personalized enough. So current way for personalization is using memory module and by tracking your conversation history and to give a little bit of personalization, but it's nowhere near the level we want. So I think that's one direction that the technology is going to evolve to, where the base generation model will have some personalized component. We'll have some like personalized parameters embedded into them. The second direction I want to mention is that in traditional recommendation tech stack, we heavily rely on this cascade modeling, where there's a retrieval stage, there's a rough ranking stage, there's fine ranking stage, and the re-ranking stage. There's multiple stages, and each of stage are separate models. So if you think about this, you will notice that the actual computation utilization is actually very low, because for every stage, there's a lot of candidates, and only a few of them pass to the next stage. And if the alignment is not right, a lot of computation are wasted. Therefore, a generative-based content recommendation process might be the next direction, where more computation power can be used to have an end-to-end solution. Just generate whatever you're going to see next. Just generate the content instead of going through this cascade modeling. So the key highlights here is the computation utilization might be better. Yeah, and I think that's the two directions I want to share that I see coming in the next few years. Thank you guys for your patience, and that wraps my presentation. And you can